So this is lesson 6.9 called Random Variables, and it's where probability meets statistics. Now, a random variable denoted by capital X is a measurable quantity which can take on a range of values or any value, and its value is the result of a random observation or experiment. Actual measured values are represented by X. This sounds really complicated, but we're going to see some examples so that you'll make sense of it. So there's two possibilities. You can either have a discrete random variable, and a discrete random variable means that you can actually make a list of the possible numerical values. And that's all sorts of experiments like tossing a coin or rolling a dice. There's only certain numbers that you can have as your answer. You could probably guess what the third one is. So continuous. Yeah, non-discrete is continuous. So continuous random variable means that you could have all sorts of values in an interval. Like the probability that somebody in the class is 5.76 centimeters. Meters.
That would be a 0.
What's the probability of that?
It's been a long day. Oh, my little elephant. Okay, so continuous random variables, you can have all sorts of different decimal answers. So a lot of times with finding probability distributions and random variables, we're going to begin with a tree or a table. So a probability distribution for tossing a coin twice. We've done these trees before. The first branch is the first toss. You can get either head or tail. And the second branch is the second toss. You can either get head or tail on the second coin. So the first branch of the tree represents the first time that you do something. The second branch of the tree represents the second time that you do something. So if I toss the coin a third time, I would just add another set of branches to each of these. And then I put the probabilities corresponding to each of the options on each branch and multiply those totals out to get the total probability representing each branch. So each branch has a 1 in 4 chance of happening. Okay, so now we're going to connect this to random variables. So I'm going to define the random variable big X as the number of heads that I get. So you see this branch of the tree? That would represent that I got 2 heads. Okay, so that branch of the tree, we can write that as the probability that X, and X is the number of heads, the probability that the number of heads equals 2 is 1 out of 4. So this is the probability that the number of heads is 2 heads is 25%. Okay, so that represents the top branch of the tree. How many branches of the tree have P of X equals to 1? 2 branches. Okay, what that P of X equals 1 means that the number of heads that I get is 1. That means when I toss the 2 coins, I only get 1 head. So either this one or this one. So that's 1 out of 4 plus 1 out of 4, which is 1/2. Okay, and then the probability that x is 0, that I get 0 heads, is the last branch of the tree. Right there. Okay, and if I wanted to, I could write that in a table too. If I want to draw a graph of x versus p of x equals x, where x goes from 0 to 1 to 2, then the probabilities are 1/4, 1/2, 1/4. And do you see what the total of all the p of x's is? Yeah, I started with 2 here because 2 just happened to be the top branch of my tree. So that's the probability of getting 2 heads. So now if I total up all these probabilities, what do I get? 1. It's 100%. And when the total's 1, that means that I have a probability distribution. A probability distribution has a sum of 1. That's the definition of a probability distribution. It includes all the possible probabilities. Okay, so really this is nothing new. It's just a new way of writing the answer. And later on this week, we're going to be graphing these things and seeing what shapes we can get. Have you heard of a bell curve? Yeah, this is a basic start of a bell curve right here. We're going to learn about normal curves and different ways that probabilities can be spread out. Exactly. So, again, we'll do the same thing. We'll draw a table of all the possible x's and their associated p of x's. We'll just make a little graph of x versus p of x equals x. And in this case, x is the number of green marbles that we get. If we have a box that has 2 red marbles and 6 green marbles. And this is nice and easy. 2 marbles are chosen and put back again. So how many branches am I going to need of this tree here? I kind of gave it away. Yeah. I'm grabbing 2 marbles at once. Okay. But I can think of that. Oh wait, no, I'm not. I'm grabbing 1 marble and then replacing it and then grabbing another marble. Okay, so with replacement means I'm taking 1, putting it back, and then taking 1 out again. So I'm going to need 2 branches of this tree, 1 for the first marble and 1 for the second marble. So the first marble can either be red or green. And then the second marble can also either be red or green. Now because I'm not putting them back, or I am putting it back. All of my possibilities is the total number of marbles, which is 8. I've got a 2 in 8 chance of choosing red, and a 6 in 8 chance of choosing green. And then to find the total probability, I just multiply the two numbers on each branch. 2 out of 8 times 2 out of 8 is a 16th. 2 out of 8 times 6 out of 8. 1/4 times 3/4. 3/4 times 1/4. And 3/4 times 3/4. Now I just have to figure out what are my possibilities for x. X is the number of green marbles that I can get. So what's the smallest number of green marbles that I could grab from the box? 0. And the biggest? 2. So I can either grab 0 marbles, 1 marble, or 2 marbles. The chance that I get 0 green marbles is 1 out of 16. The chance that I get 1 green marble, 6 out of 16. You can simplify that fraction if you wish, but this helps me to see that it all adds up to 1 if I keep the same denominator. Chance that I get 2 green marbles, 9 out of 16. And if I add all those numbers, 1 plus 6 plus 9, the total is 16 out of 16, which means I must have done it right. Okay, so another way to write this is that the probability that the number of green marbles is 2 green marbles is 9 out of 16. So that's what this whole terminology means. Okay, we'll just do that one last example and then we'll do the next step later. Tomorrow. So this last one, we're trying to find the difference between one dice and another dice. We're throwing 2 dice. There's so many possibilities. 1 and 6, 1 and 5, 1 and 4, 1 and 3, 1 and 2, 6 and 6, 5 and 6. We wouldn't want to do this in a tree. So let's do it in a table form, where we have the first die and the second die. So we can either roll 1, 2, 3, 4, 5, or 6, and on the second die, and then inside the table, we can fill in what the differences are. So the difference between 1 and 1 is 0. The difference between 2 and 1 is 1. What's the difference between the two numbers? The difference between 2 and 1 is 1. The difference between 2 and 2 is 0. Okay, so in each of those entries in the table, we'll put the difference between the two dice. So in this one, there's a lot more possibilities. We can make a graph of x versus p of x equals x. The difference between the two numbers has this really nice pattern to it. It has zeros down the diagonal. Okay, so the smallest difference between the two dice is 0. And the chance that the difference between the two dice is 0 is 1, 2, 3, 4, 5, 6 out of 36. Okay. Or you could have a difference of 1 between the two dice. The chance that the two dice have a difference of 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of 36. The probability that the two dice have a difference of 2 is 8 out of 36. And this is kind of a nice pattern here. The largest difference that you can have between the two dice is 5, which is 2 out of 36. And if you add up all those numbers together, you get 1. Beautiful. So you can write any one of these as an example. What's the greatest probability? Having a difference of 1. And that's a 10 out of 36 chance. So for practice, take a look in your textbook, page 522, numbers 1, 3, and 6 to 10.